Hello, welcome to our functional safety training. My name is Markus Rau and I'm the responsible training manager in our Competence Center for Functional Safety within SGS-TÜV. Today I want to introduce you in the world of functional safety, and then I will show you the implementation of ISO 26262 for the semiconductor development. So now let's start our presentation. The presentation will take around 1 hour and the content is the following. First chapter, a short introduction into functional safety to understand what we're doing here. So the second one is introduction into ISO 26262. I will show you where it's coming from, what is the scope, and so on. The third chapter is to show you the most important implementation blocks for the semiconductor development. And finally, we will summarize what we have seen in this presentation. But first of all, we have to do some definitions to understand functional safety. So the definition of functional safety according ISO 26262 is given as follows. Absence of unreasonable risk due to hazards caused by malfunctioning behavior of EE systems. Yes, so this is a complex sentence with, again, some new expressions which I have first to define and which I have first to explain. Because what is the definition of unreasonable? What is the meaning of unreasonable? So yes, we can say unreasonable means unacceptable. So it's unacceptable for the most of us. That means unacceptable for the society. What is the definition of risk? So this is very important to know, because the risk is a combination of two things. It is a combination of the probability and the extent of damage. So that means, of course, both probability and extent must be small or low to have a small risk. So we can get a high risk even if one of these components are high. Yes, if the probability is high that something happens, that the damage will happen, then the risk is maybe high, or if the extent is high. So at the end of the day, we'll see that the probability is the most important point for us, because if we can reduce the probability to a very low level, so we can make the risk acceptable, or what is then defined by the standard reasonable. And finally, the definition of hazard. What is hazard? So I define it with, in my own words, with state which may be dangerous for health and life. So this is also important to understand. If we talk about functional safety, then we talk about, yes, health and life. So nobody shall be injured or even dead. So now let's coming back to the definition of functional safety. Maybe you will understand it now a little bit better what we do. So we have a malfunctioning behavior of EE systems. That means whenever we bring electronics in vehicles, so we have the potential that this electric may have a failure, yes, may have a malfunctioning behavior, and this may lead to hazards. This means, according to our definition, the malfunctioning behavior of the electronics may lead to a state which may be dangerous for health and life. So, and whenever we can reduce the risk to a reasonable level, yes, that means absence of unreasonable risk, yes, due to these hazards caused by malfunctioning behavior, so we achieve safety, we achieve functional safety. So, with other words, what we have to do, we have to reduce the risk to the reasonable or accepted level coming from our electronics. Then we achieve functional safety, or we achieve an accepted level of functional safety. So here it's shown in a graphic way. You see the severity of harm caused by EE system malfunction, and on the left hand, the probability of the occurrence of harm caused by EE system malfunction. So it's not a question, first of all, what is probability of the malfunction itself. It's more the probability that the harm will really occur, or that it's really get dangerous for for life and health of people. So both things, the severity and the probability of occurrence, will bring us in an unaccepted level or an unaccepted area, and this means we have to reduce the risk to the to come below this risk acceptance limit. So this is what we have to do if it's unaccepted, or with other words, if you bring electronics in vehicles where we have no measures to reduce the risk to the accepted level, it's maybe unacceptable, and at the end we have to implement measures to make it acceptable. And this is the reason why standards, and especially here ISO 26262 for the automotive industry, is introducing a level of risk. Yeah? So this is the so-called ASIL. I think most of you have heard about it, the Automotive Safety Integrity Level, ASIL. So it's not called a risk level. So, and we'll see now why. So first of all, to understand what it is a 5-step scale. The lowest level is QM, then ASIL A, B, C, and D. QM here means that a standard quality assurance is already sufficient to reduce the risk to the accepted level. Or in other words, that the risk which we bring with electronics in the vehicle is acceptable by using standard quality measures. But this is very important. Quality or quality measures according to standards like IATF or ISO 9001 have to be established. Yeah, so this is the minimum which is required. If we find out that we have an ASIL X means ASIL A, B, C, or D, this means additional risk reduction measures are required. Additional means additional to the QM measures. The QM measures, the quality measures, are already maybe a high level to reduce the risk, but additionally to this we have to add measures. The ASIL then describes the required integrity which has to be achieved by the determined safety goals. So we have to know that coming from the risk which we have to identify in the vehicle, we have to define so-called safety goals. And these safety goals then will get the ASIL. So first of all, it is a risk level, but then it is a requirement to achieve a safety goal with a defined integrity. And this is, I would say, this is the kind of spirit of functional safety, yes, to define safety goals for the vehicle and to achieve these safety goals with a defined integrity, and the required integrity depends on the risk, of course. Or with other words, if we have an ASIL D, for example, as highest level, so we have to achieve our defined safety goals with the highest integrity due to the fact that we have a high risk behind it. So let's make an example. So if we look at a functionality which is called driver airbag, yes, so driver airbag shall deploy in case of an accident, yes, to help the driver maybe to survive, yes, to reduce the risk of injuries. So about this driver airbag, which is driven by electronics, of course, has the potential to deploy unintendedly. That means during normal driving, or it has may have the problem that it will not deploy in the case of an accident. Let's have a look on this unintended deployment. Unintended deployment during normal driving may lead to loss of to the loss of control over the vehicle, and this may be dangerous, of course. So the result may be an accident. So this is typically defined with ASIL D. So it's a high level of risk that an accident will occur if we have an unintended deployment of an airbag. The safety goal, which is then derived, means an unintended deployment shall be avoided. And this safety goal, the unintended deployment shall be avoided, must be then achieved with an integrity of ASIL D. That means QM is not sufficient. We have to do a lot of things additionally to reduce the risk to the accepted level. So, and then here the last bullet point shows it, is that the ASIL is then inherited to the derived safety requirements. From these top level requirements, which are called safety goals, we derive then detailed requirements on all abstraction levels going top down from the vehicle level to the functional level, system level, going down to hardware and software level. And all these requirements which are derived will inherit typically the ASIL. What does it mean? Each requirement which has inherited the ASIL means that it has to be achieved with this defined integrity, nothing else. And this is very important to understand, that the ASIL is not a product property. Yes, many people think it's a product property. No, it's depending on the defined safety goals, and it's depending on the risk behind. And the ASIL never stands alone. The ASIL is always combined with the requirement. This should be clear in any case, otherwise you will never understand how ISO 26262 is working. So here in a graphic way, then it's shown. So if we combine again probability and severity of harm due to a malfunction caused by EE system malfunction. So if we far away from the risk acceptance limit, so the risk is high, like ASIL D, but this means also we have to do a lot of effort to reduce the risk, or with other words, we have to do most additional things to make it acceptable. So now, how shall we now achieve functional safety in automotive functions and systems? The first point here on the top is to analyze the potential hazards and to assess the risk. That means, first of all, we think about our potential malfunctions, yes, due to a malfunction of the electronics, like this unwanted or unintended deployment of the airbag. Yes, so this is the hazard. And then we are assessing the risk. What is the risk behind? So what is the probability of the accident at the end, and what is the extent of the damage to people? So this is also called HARA, Hazard Analysis and Risk Assessment. Here shown with this HARA, HARA, Hazard Analysis and Risk Assessment. So this is always the point which we have to do, or the activity which we have to do when we bring new functionalities in vehicles driven by electronics or electrics. So then the question is, if the ASIL is equal or higher than A, means ASIL A, B, C, or D, then we have to do additional measures to reduce the risk to the accepted level. If we can say no, if the result is QM, then standard quality management is sufficient, as already shown before. This does not mean that this malfunction will never lead to an injury to people. This only means that the risk can be already accepted by using quality management. So let's go on here. We say ASIL A, B, C, or D, additional measures to reduce the risk to the accepted level. What we have to do now to achieve it. The first is the avoidance of systematic faults in general. Of course, we have to know what are systematic faults. So systematic faults, we can say in general, these are the faults which we bring in the product by our own doing, yes, by a bad specification, wrong specification, by missing something in the processes, by missing something during the testing, and all these things, yes. This means systematic faults means if we have then a fault in the product, then all products have the problem that they have the same fault. And of course, highest target is to avoid these systematic faults. How can we do it? Yes, we have to implement safety management, then so-called development processes and supporting processes described in ISO 26262. This means ISO 26262 tells us what we have to do additionally to QM. And this is what we also call, this is a process focus. So many people say ISO 26262 is a process standard, yes, because we have so many processes which are described, which we have to follow. And the target is really to avoid systematic faults. On the other hand, of course, we may have faults which we are not able to avoid it, or even in the hardware we will find so-called random faults. Yeah, so per definition, hardware may fail randomly. These are called random. Random and systematic faults we may have during operation. So then we have to control it. Control means we have to detect the faults and we have to react on the faults. That means if the fault, which has the potential to violate a safety goal, will occur, we have to control it in the time which we have which we have available. Yeah, so of course it can get very dangerous. So if we think we have a fault in the electronics which may lead to an unintended deployment of the airbag, as an example, of course, then it takes, I think, a few milliseconds that the airbag will deploy unintended. And this is a time which we have typically to detect the fault, and to react it means to switch off the airbag activation. And this means control. Yes, and control means then we need requirements to function, system elements, hardware, and software. And this is also described in ISO 26262. So this is then nothing else than to derive detailed requirements top down from the safety goals down to hardware and software, and to implement it in a technical way. And this is what we call the technical focus. Yes. At the end of the day, of course, we will then find in our systems and in our products many so-called safety mechanisms. And safety mechanisms are nothing else than mechanisms to detect and to react on faults. That means to control faults coming from this random and systematic faults during operation. So let me summarize. We have to do two things. Follow processes, safety management, development process, and so on. And on the other hand, we have to implement technical features to control faults. And of course, ISO 26262 makes then the difference between ASIL A, B, C, and D. And this is the result is then can be seen in the effort, of course. So ASIL D means then we need the highest effort to implement the processes and the technical requirements, because we have to reduce the risk on a very high level, of course. Now everybody should understand what functional safety is and what is what we're doing. Yes, we reduce the risk to the accepted level, nothing else. So let's go on now with the second chapter, Introduction into ISO 26262. Here I want to explain a little bit more around ISO 26262, where it's coming from and how we use it. So first of all, the title, Road Vehicles in Functional Safety. That's clear, but it's very interesting because it is a standard really for road vehicles. So there are several other standards available for other vehicles like forestry, agricultural machines, and so on. So there are different standards in the market, and ISO 26262 is mainly for passenger cars, and of course now since edition 2 for also for commercial vehicles and motorcycles. So it is a standard which is for safety relevant systems where we have one or several EE subsystems. That is important, and I think this is what we already have seen in the definition of functional safety. So we talk about electric electronics. Whenever we have electric electronics in a vehicle, so of course automatically we have to talk about ISO 26262. So special vehicles are excluded, so like vehicles for disabled persons and so on, there are different other standards or regulations are available. So, and again, it deals with possible risk arising from the malfunction of the EE system itself. Yes, means caused by the respective EE system itself. So it is not a question whether we need an airbag, whether we need safety systems like ESP, ABS, whatever else. So ISO 26262 tries to clarify what happens if you bring electronics in a vehicle. It makes no difference between a safety system or non-safety system, yes, or comfort systems, yes, but asking, oh, what will happen if we have a malfunction? Is this a risk for persons, and can this risk be accepted or not? So, and here below what I already said, edition 2 now includes also motorcycles and commercial vehicles, which was not in the edition 1, where motorcycles and commercial vehicles were excluded. So the architecture of the standard, what you see here is a big V and then two small V's. So we can say it follows the typical way of development in the automotive industry, to follow a V cycle. There are several parts. So what we find in ISO 26262 now in edition 2, there are 12 parts inside. So here on top we see part 1, that's a vocabulary where all the definitions and abbreviations are explained. Then the management of functional safety, it's part 2. Part 3 is so-called concept phase. So we will also find the HARA, the hazard analysis and risk assessment. Part 4 talks about the system development, 5 hardware, 6 the software development, and 7 about production operation. So far so good. So we have some additional parts. Part 8 gives us supporting processes. I will come later to this part. Come back later to this part. Then part 9. So the ASIL oriented and safety oriented analysis. Yes, all this FMEA, FTA stuff and so on. Part 10 is nothing else than a guideline with some more explanations, with some examples. And part 11 now the interesting part for the semiconductor development. Part 11 is a guideline or application of ISO 26262 to semiconductors. So be careful, it's only a guideline, it's informative. So part 11 tries to explain some more about the semiconductor development and how the other parts are typically to be used in the semiconductor development. And finally, we have also part 12, which is here shown on the left side. It's specifically done for the motorcycle development, where are some, yes, I would say some simplifications are done to make life easier for motorcycle electronic development. So what we can say, the new part 11 gives a guideline for the semiconductor specific interpretation of the standard. So that means we're using the standard as it is, typically the parts 2, 3, 4, 5, 6, 7, yes, and part 11 gives us really a guideline, gives very good examples, so it makes sense to look inside because there are good examples given how we can manage the requirements and how we can fulfill the requirements, of course. So the question which very often comes is, what are the legal aspects of ISO 26262? So is it mandatory? Is it really a law to use it? So what we can say immediately, no, it's no law. Yes, so it's not mandatory to use it for approval, for example, type approval. Like in Europe, we have this EC directives and the EC regulations for the automotive industry. So this is not the same, yes, and ISO 26262 is not mentioned here. What ISO 26262 is here mentioned on the right side, it's a technical recommendation. A technical recommendation, that means it's recommended like other standards, IC, ISO, EN, DIN, and so on, other standards recommended to achieve the current state of the art. The current state of the art in functional safety development, of course. And here it becomes to be relevant. Yes, ISO 26262 is worldwide seen as, yes, as a kind of standard. It is accepted from all members of the ISO, yes, and can be seen as kind of the state of the art. So the legal consequences, if we know this, are then the published ISO 26262. This means the normative parts 1 to 9 describe a kind of state of the art. So it's typically used to say, yes, this is state of the art in automotive functional safety development, which shall be achieved. Even if it's not mandatory given by law, but yes, we have no other standards available and it's accepted worldwide. And product liability laws do not really reference to this standard, but they require state-of-the-art developed products when placing in the market. So it's important to know. So that means whenever we bring a product in the market, we have to ensure that it is developed according to the state of the art. And now the question is, what is state of the art for functional safety in automotive? Yes, we can assume. Yeah, so that's our estimation. If we follow ISO 26262, then we do most things which are expected to fulfill the state of the art. So what we can say is ISO 26262 is an important argument for achieving the state of the art in functional safety. And this is, I think, the reason why OEMs, car manufacturers require these standards from their suppliers, of course. Yeah, they say, okay, please develop it. And I know it from some big OEMs, they do not ask for ISO 26262 from their suppliers, they ask for state-of-the-art development because in the background is the product liability laws. And what you can do, of course, follow ISO 26262. So how does the standard now work? So typically, of course, at the end of the day, we need a vehicle, here a car is shown, which has implemented many functionalities which are functional safe. Remember what we said? The risk is reduced to the accepted level in all these functionalities due to their potential to get malfunctions in the electronics. So these functions, or these functions which are safety related in the vehicle, are typically called items. So this is already an expression from ISO 26262. So we have item 1, item 2, and so on. Item 1 is a driver airbag, item 2 is a low beam light, item 3 is a brake system, and so on and so on. Yes, many items which we have, and these items must be safe or functional safe at the end with their EE components inside. So what we already seen is that we have to derive in an HARA, typically in an hazard analysis and risk assessment, safety goals. That means for all these safety related items, we derive, or we define, we determine, can say, safety goals. So that could be one safety goal, 2 or several safety goals per item. So remember what we said for the airbag, driver airbag, we said, okay, it's a driver airbag, and the safety goal 1 was an unintended deployment shall be avoided. ASIL D. And another safety goal for this item, driver airbag, could be the airbag, the driver airbag shall deploy in the case of an accident. Maybe only ASIL A. So you see, the safety goal depends directly on the functionality, and of course the ASIL which we get is typically from the HARA, from the hazard analysis and risk assessment. So the next step typically is to derive from the safety goals detailed so-called functional safety requirements. Yes, to achieve the safety goals. We describe on a functional level how we try to achieve safety goals, like faults shall be detected, faults shall be detected within a specific time, so the reaction on faults shall be done in a specific time, Yes, switch on power, off power in case of this and this. If speed is higher, so and so, then do this and this. So these are typically functional safety requirements, which are typically directly derived from the safety goals. And what I already mentioned before is that we typically inherit the ASIL. That means one safety goal typically has several functional safety requirements derived with its specific ASIL, of course. The next level is then the technical level. And the technical level is then a level where typically also the development of the semiconductor start. So from these functional safety requirements, typically technical safety requirements are derived. That means once functional safety requirement where it was written faults shall be detected, then we describe it on a technical way. Technical safety requirements, faults in the memory shall be detected by using an ECC, for example. Yeah, so these are then technical safety requirements. And this is then the level where we typically start on hardware, on software, where we give these technical safety requirements down to hardware and software development. So with other words, if we do not know our top level technical safety requirements, we have to assume it by ourselves. And if we do not know the final case, the final item, the final vehicle at the end, so where we bring in our semiconductor, so we call this safety element out of context development. So we have then to assume these top requirements, these top technical safety requirements. Yeah, we will say, for example, the output shall not have an error higher than this and this. Could be a technical safety requirement. This is assumed, where we assume this is needed to fulfill the higher requirements, functional safety goals within the item. This is what we typically do. But to understand what we do, typically it's a top-down approach. From the vehicle, top-down, the safety goals which shall be achieved, and then we derive requirements. And if we do not really know the final use case, so we have to assume it by our own. And this is typically very often done in the semiconductor industry, where these technical safety requirements are not coming from a real customer, though these technical safety requirements on top level are assumed by the semiconductors developers themselves, by market analysis, by asking some potential customers, and so on. So this means this is a level where we typically start, and what I very often call it top level safety requirements. These are then the highest technical safety requirements which you typically derive or assume for the semiconductor. So this was a short introduction now for functional safety. Remember what we're doing. We do a risk reduction. This is why functional safety is also very often called the risk-based approach. And ISO 26262, which has the idea, okay, we have safety goals, we derive top-down requirements, and we have to implement it within our products. Now let's talk a little bit about in more detail about the semiconductor development. I want to show you some most important blocks which shall be implemented to be in compliance with ISO 26262. Of course, I think the standard has more than 300 single requirements, and I cannot explain it here. I can give you only a short overview, of course, to understand what are the main blocks. Yeah, so I call it also building blocks for functional safety. So let's start with the so-called functional safety management. Remember, functional safety management was one point to avoid systematic faults. The second one will be then the safety relevant activities during the development. So along the V-cycle model development, remember we follow typically requirement management, verification steps, and so on. Yes, we have to do some additional things to our standard development process. Then the safety relevant activities during the production could be relevant. Yes, so we'll see what is described here. The safety analysis, very important point to understand. So because safety analysis helps us to verify our design and to find, of course, faults specifically systematic faults in very early phases of the development. And finally, the so-called supporting processes. So that means additional things which we have to do as an add-on to our quality management process, yes, to, let's say, to increase the quality more than it is at the moment with your standard processes. Let's start with the functional safety management and look a little bit deeper inside. What is it? So typically, functional safety management is based on quality management. And this was the reason why the lowest level, remember, in NHARA is QM. Yes? The basis is always QM. QM must be fulfilled. Or with other words, no functional safety without quality management system. And on top, for ASIL A, B, C, and D, ISO 26262 requires this management of functional safety, which coordinates the requirements to be met by functional safety. So here below, we see it in the overall architecture. It is shown in part 2. This means this ISO 26262-2 in 3 chapters. So ISO 26262 shows us the overall safety management, which is typically the management which has to be implemented in your company with all the processes, tools, templates, process descriptions, and so on. In the chapter 6, 2-6, the safety management during the concept phase and the product development. That means the safety management which has to be done during the development itself. And the third part is the safety management then after the items release for production. It means after SOP, that means after, after tape out, which we have to follow typically. So in all these 3 chapters, we will find requirements to be fulfilled. And we will also find some, not all, let's say some which are different depending on the ASIL A, B, C, and D. Let's go on with the next building block, the safety relevant activities during the development itself. So now the question is how to develop functional safe semiconductors. So what we have seen, okay, you follow typically your standard processes, which are, I assume, on a very high level, yes, on a high quality level. And the semiconductors typically are standing on the starting point of the supply chain. Yes, you supply your semiconductors to customers, your ICs or your IPs even to your customers, which require or which expect that you fulfill the requirements according to ISO 26262. So typically, semiconductors are not especially considered in the system development process of ISO 26262, but we will see that we have to start here. And it's also not covered especially on part 5. Yes, so this was the reason why ISO 26262 now added additional considerations in ISO 26262 part 11. How semiconductors are to be handled and gives, for example, failure modes, things which we have to do, analysis, examples, and so on for the semiconductor development as an example to understand the part 4, part 5, and if software is included, even part 6. So, in my opinion, the typical development steps or additional steps for functional safety for semiconductors are always the same. So, step 1 describes the initiation of semiconductor development and definition of scope. Of course, what is the scope? What we will develop? Is it an IC? Is it an IP? Yes. Which application is it used? Use cases and all things around. And then we are already in step 2. Step 2 describes assumptions on safety requirements at concept and system level. Concept level here means really on vehicle level and on system level. So assumptions, or of course, maybe you will get this, get real requirements from customers. But very often we call it here safety element out of context development. That means we have to define assumptions. Yes, we, for example, define it by ourselves. Say this semiconductor shall be used in an airbag application, yes, where the safety goal is this and this, where the ASIL is this and this, where the requirements are this and this. Yes, these are assumptions which we first have to do to be able to derive requirements. And this is step 3. In step 3, we derive safety requirements on system level first. Yes, on this highest level, what is required. Yes, here also we typically require already probabilistic target values, the so-called hardware matrix. Maybe you've heard about it. And we do the design, the system design. Yeah, so chip design, for example. Step 4 is then nothing else than one abstraction level below. So we derive more and more requirements top down to hardware and software level, and yes, and make the design for it, of course, to fulfill these requirements. And step 5 is typically then the integration and the testing, of course, the right leg of the V cycle. Maybe you will say, yes, this is what we typically do. We derive requirements, we make a design, and we make the integration and testing. And you are right, this is not different to your standard development typically. But we have additional requirements, maybe derived from the safety goals top down. We have these additional requirements have the ASIL, and depending on the ASIL, ISO 26262 requires to do several things. For example, to show that the hardware matrix typically are fulfilled, or to follow in the software specific processes using techniques and measures depending on the ASIL, and so on and so on. Or for the testing, to use specific test mechanisms, test methods, depending on ASIL, and so on and so on. And this is then the difference and what I call the add-on for ISO 26262 development. That means, in the best case, you have not to change your already established development process, but you will get several add-ons what are required from ISO 26262. So at system level, typically we can say we have two different abstraction levels. So typically we start the first level in our application circuit. Yes. So where is the chip, for example, used in which application? Yes. For example, the airbag application in a control unit and so on. Yes. What are the inputs, outputs to understand the functionality and the requirements on the functionality of the semiconductor? The second level is then the chip itself, typically. Yes. And here it's shown in a functional block diagram to show it with its block, with its functional block. Yes, I call it the system development here for the semiconductor. So this is typically then the interpretation of it. On hardware and software level, then we go one step down, yes, in the abstraction. So we go on sub-block level, yes, standard IPs and so on. And the second level is then really to go inside the hardware and the software, the implementation on gate, transistor level, and of course on software level. Yes, so then we talk about part 5 and part 6, where we, especially in the part 5, then have to show that the so-called matrix are fulfilled. And if we cannot fulfill this matrix, we have to add maybe some technical features to be able to detect more faults and to control more faults. And the same procedure in software level, but software, then there are no matrix are to be calculated. On software, you have to follow a detailed software development process with all ASIL dependent methods and techniques to be used. So for the hardware, here is a process model. Yeah, so this process model is still from the edition 1, but I think it's not very much changed. Only this 5.5 has been shifted to the other part. So what we can see, we come typically from the system design, from our chip design. We derive it down to a specification of hardware safety requirements. We do the hardware design, and the most important points are these probabilistic calculations, which are typically done with FMEDA called failure mode effect and diagnostic analysis, FTA fault tree analysis, and also here the dependent failure analysis, which is typically required. That means on hardware level, we can say the most effort which we have is really to show that the target values of our matrix according to the ASIL are really fulfilled. So on software, well, the standard software level has this V cycle with these several steps. I think it's also not very new for most of the software developers, but we can also say here within these blocks and steps, we have ASIL dependent requirements shown in many tables of ISO 26262 part 6, of course. So let's go on with the next step, the safety relevant activities during the production. So what we can say for semiconductors, the basis is typically are the AEC-Q standards, 100, 200 typically. And of course, to follow our quality standards like ISO or now called IATF 16949 requirements. So which are also mentioned by ISO 26262. What we typically have additionally is the planning of so-called dedicated measures. Dedicated measures we always need if it is required from the development. Yes, to do a burn-in test, for example, to have oversizing, yes, over voltage sizing here called, or define how to handle necessary modifications and so on. So what we can say in the production, there are no ASIL specific requirements are given. So we need a way to handle requirements from the development, coming from the development, even during production, if necessary. So it has to be ensured that all implemented safety mechanisms are working correctly. So, and there are examples are given in ISO 26262 part 11. So the safety analysis. So the safety analysis can be seen, yes, as a necessary analytical verification method. Yes, maybe you know FMEA and such things, which help us just before we do the testing typically to find faults in very early stages of the development. So ISO 26262 knows in the part 9, it's mentioned here, part 9, 3 different analysis or kind of analysis. So the first is the analysis of the interdependency of elements. Yes, so we call it also freedom from interference has to be shown. It's to be performed if there is a need for coexistence of different ASIL requirements. The other way is to handle everything according to the highest ASIL. Yes, then it's not required. But if you decide that you have different requirements with different ASIL, then we have to do a so-called freedom from interference analysis. The second point is to do an analysis of dependent failures. So here it's necessary to identify the so-called common causes and the cascading faults. And it can be seen as mandatory. Mandatory, especially on the semiconductor level, to be performed, especially to argue for the so-called ASIL decomposition. So this is a special technique which allows us to reduce the ASIL due to redundancies. But I would say a DFA is in any case necessary because also the functionality and its safety mechanisms should be independent, also in these cases. So you could remember that a DFA typically is part of a semiconductor development. And finally, what is typically very often already done, the analysis of faults with the potential to violate safety goals for the design verification at system level, hardware, software level, with methods like FMEA, FTA, and so on. And then what I've already mentioned before, for the hardware, we have to do the probabilistic evaluation. Yes, really do probabilistic calculation, which is done with a method which is called FMEDA, failure mode effect and diagnostic analysis. Yes, to really to calculate at the end, or to be able to calculate at the end the metric hardware metric values, which are what is mandatory for ASIL C and ASIL D to verify system and hardware design. So this is a typical table, yes, from the standard. So the standard do not really require FMEA or FTA. These are only examples. You see the plus for ASIL A, B, C, and D. An inductive analysis has to be done on hardware, on system and on hardware level. Could be seen mandatory. This was what most companies already doing, FMEA at system level and hardware level. A deductive analysis like an FTA, so which follows a top-down approach, typically we see the plus can be seen as mandatory, or the standard call it highly recommended for ASIL C and D additionally. So here typically shown how this hardware matrix evaluation is typically done in semiconductor area. So the known method I already mentioned before is FMEDA. So what we do, we show the robustness of hardware architecture according to the ASIL, what is required. And at the end, the total safety goal violating failure rate can be shown. So how it is done? It's an FMEDA, so this analysis is done at IP level. The result from this IP FMEDA is typically the input to the FMEDA at IC level. This is why IC suppliers very often now require from their IP suppliers to get the results from the FMEDA to be able to fill in the numbers in their FMEDA. And the result of the IC level is then typically given to the system provider or to the item level, where then it's possible to do this calculation on system level or on item level, and to show that the metric values are really fulfilled. And this means the system or the function, or the standard then call it the item, is robust, sufficiently robust enough. So, and the last building block are the supporting processes. Also very important. We have seen process focus. We have to avoid. So here are the supporting processes shown. In addition to, there are two new, but these are only relevant for commercial vehicles, or let's say trucks and buses typically. So what we see here, these are typically things which have to be followed and implemented, like interfaces with your suppliers, project management, things like configuration management, and so on. I want to pick out only one of it, because this, I think, is an important point. This is very new to follow. Confidence in the use of software tools. So this is so-called TCL assignment. This means for all tools which we're using in the development, yes, development tools, verification tools, requirement tools, all software tools which we use in our development, first we have to do a kind of classification in a tool confidence level. How confident is this tool? And the standard gives us a method. The method is working in that way that we first have to identify the so-called tool impact. Has this tool really an impact on functional safety? And the second point is, do we have the chance to detect errors in the tool itself? Maybe within our development, in our process, in a later step of the process, where we say, okay, if the tool would make a fault, yes, so we will detect it during testing or something else. This is then covered by the tool error detection. And so the standard knows 3 TCLs, tool confidence levels. TCL 1 is the best one, shown here in green, where the standard says if we achieve TCL 1, so there's no qualification of the tool necessary really to be done. Here in this picture, on this table, ISO 26262 says, okay, for TCL 2 and TCL 3 tools, we have to do an additional qualification. And here are 4 methods are mentioned. So the first 2, can be used for a TCL 2 tool up to ASIL C. Typically, you see it here with the plus shown in green. And for TCL 3 tool, only up to ASIL B. The third and the fourth one can be used in any case, but maybe it's more difficulty to realize it. Yes, like 1C is a validation of the software tool. To validate it, that means we need a detailed testing. But this is only to give you an example. Of course, I will explain, and our experts will explain this much more in detail, and we have some very good examples and exercises where you can train it in our detailed trainings. So I think this was it in general. Yeah. So let me do a short summary. Yeah. So I tried. So this is, of course, it's not complete. So I tried to summarize typical output documents for semiconductor development. What we need typically to fulfill ISO 26262. We have to do a so-called function safety management. Yes. That means everyone who has to work according ISO 26262 has to fulfill the requirements according part 2 of the standard function safety management. So what are typically work products or output documents are the so-called safety plan, where we plan all activities. A functional safety assessment plan, where we plan how to assess and who will do at the end an assessment whether functional safety is achieved or not. A functional safety verification plan, detailed planning how the verification has to be done by the use of analysis, by the use of testing, by the use of calculations, by the use of reviews, and so on. And the tool qualification is also a very important point, which is always necessary to list all your tools which you are using in your project, and if necessary, also to have the reports for their qualification. At system level, yes, for the development phase system, so we typically need, yes, at system element level, assumptions at system element level. So this is what I already mentioned before. We have to do some assumptions. What is the safety goal? What is the application? What is the ASIL? Yes, typically for the semiconductor, if you do not get it in detail from your customers, you do your own assumptions. You say, I develop a chip which is used so and shall fulfill this requirement with this ASIL. So this is your assumption. And then one level below on semiconductor applications, semiconductor functional block level. So we have then to derive safety requirements. This typically ends in a safety requirement specification. We have a semiconductor design on this highest level. We do a design verification with reviews, FMEA, FTA, simulation. We do a system integration documents or system integration testing. We need the documents for it. We have a safety requirements for the production if necessary. And very important, typically we have also a safety manual for the integrator of this system. On hardware level, that means on semiconductor block and IP level or gates and transistor level. So we go one step down. So that means we derive more detailed requirements to be able to do the design on hardware level. So, and then again, we have to do a design verification with reviews. We do this so-called FMEDA. Remember, this was this probabilistic calculation. We do the simulation. And then we need the system integration documents. And finally, we refine our safety manual for the integrator, that the integrator knows what he or she has to do to fulfill the required integrity and to fulfill the required safety goals at the end. For the software, at software application level, of course, the software documents shall be available which document all methods and techniques which are used to fulfill the software safety lifecycle required from ISO 26262. So this is, of course, only short to get an overview. That, of course, there we need additional documents typically, and this is typically done at the beginning where we do the planning. What are really the add-ons which we need to fulfill ISO 26262? So I think this was now sufficient for the moment. Yes, I think it was very much. But you should have now an impression, yes, what ISO 26262 wants to have. Of course, starting what is functional safety and then how ISO 26262 is implemented. And of course, you need much more details. For these reasons, we provide a 3 days training program. Yes, of course, you can also book single modules alone if you I think only module SC1 is interesting for you, or SC2. So there are 2 modules. The first one is only 1 day, where we go deeper inside in the processes again, function safety management, and in detail the processes which has to be followed. And then in module SC2, we yes, I will show you to the implementation of ISO 26262 in a real example. So we will take an example. So it will be of course, a simple Hall sensor or something like this, and then we will go through all the steps to show what has to be done and how the so-called work products, the documents according ISO 26262 can look like. So this is what we do here. And after these 3 days, you have the chance, if you want to do it, to do a qualification, which we call semiconductor AFSP, Semiconductor Automotive Function Safety Professional. So you can do then an online exam, which takes around 1 hour. Yes, it's a multiple choice test. So, and if you're passing this successfully, you will get a nice certificate with this SC AFSP title, which is valid for 3 years, typically. Yes, more information you will find here on our homepage, www.sgs-TÜV-SAR.com/FS-training. Yes, here you will find all our trainings, and then look for semiconductor trainings, and you will find all these courses. Of course, you can send also an email or contact us directly if you have more questions. Here are Munich and our Dortmund addresses. So in both offices we have semiconductor experts sitting. Here you see the phone number. If you call this phone number, you will contact our secretary, and the secretary then will see who is available and can call you back or directly answer your questions. Of course, you also can send an email to our email addresses, which are also shown here. And if you're interested to come in contact with our affiliates, especially in Japan, in China, in Korea, and also in the USA, of course, then we can give you the addresses and the contact persons if necessary. So now we are at the end, and I would say thank you for attending. And yes, it would be nice to meet some of you in real trainings. What I want to say, we can do all trainings also online and on trainings where we come to your companies. And of course, if you look on our homepage, we have also some trainings, public trainings, where we can come to Munich, Dortmund, or Stuttgart, and also trainings worldwide in the offices of our affiliates. So feel free to contact us. So again, take care. Yes, and I would be happy to meet some of you. And yes, what I want to say, it's good luck in using functional safety and yes, ISO 26262. Bye bye and see you. Okay.